But want to introduce briefly the tensor notation. I probably will go through this much quicker than usual, and then the textbook even, because we are running out of time. And then we'll hopefully repeat that in math physics. Okay, so now we'll introduce this language. First, it will be a little uncommon that we'll use the superscript as the index of the components of the forward. This is a contravariant vector, so we use superscript, say x2. Let's see what x we use. X use grid ladder, so x alpha. Alpha goes for, so alpha is 0, 1, 2, 3. That will, the 0 is the time component, so that will go to this is the t component. And Jackson actually 1 is the z axis. So you see it. Right. So anyway, we'll define this contravariant forward vector in the sense that this is c times t, and then you have c. Okay, that is the what you call contravariant, and the transformation between contravariant vector is like for this spatial space-time forward vector. Yeah. These are all linear transformations, so we can write that as like the derivatives is partial x pi out x beta and x beta, and using the Einstein notation with repeated index, but the repeated index has to be 1 in the superscript like this contravariant, and the subscript. This is this is a superscript in the denominator, and when you put a superscript in the denominator, we call it a subscript. So you sum over a superscript and subscript. That is actually just a summation. We ignore the summation sign. Okay. So and this is like a matrix multiplication. You treat this as a column vector instead of a row vector, right? Then this is a 4x4 matrix, and in our case, this 4x4 matrix is just the Lorentz invariant. Just write it as use. This is a scalar, and there's lots of 0, and then the perpendicular component is just unchanged. This 1. Okay, so that is the transformation matrix, right? And that is what we call the contravariant vector. Let's see what order of discussion in Jackson. So any, and then by this we extend this concept to any vectors. Any vector transform like that is contravariant for vectors in any vector A with index alpha. If it transforms just like that, the same Lorentz transformation. We satisfy this, and this is also a 4 vector. Okay, and contravariant form. And likewise, we can extend it not just vector. We can have an object with 2 index. Like if you have 2 indices, then it becomes a matrix. Actually, in this case, 4x4 matrix. Like you have B, pi, alpha, beta. Then it transforms with 2 Lorentz invariant matrix with partial x, pi, alpha. You already beta, so you use the gamma, beta, delta, and delta. Now it's sum over gamma and sum over delta. So you have two matrices. Okay, and this is also like matrix multiplication, but this matrix multiplied by this one and then multiplied by that. We reverse this order, the order of these two, that becomes the matrix multiplication. Okay, and all right, then obviously you can keep going. This is called second rank tensor. You can add more indices from third rank, fourth rank, and so on. But each increase, you add another transformation matrix to define whether it's a four vector or four tensor or not. Okay, and now after this what we call the contravariant vector, contravariant four vector. Also wanted to define the covariant four vector. The covariant, now we are using subscript, right? Covariant. And for this space-time covariant four vector, it turns out that just change the sign of the space. Minus C, minus. Okay. And this covariant four vector transform differently, so it's not transformed this way. It actually transform in like an inverse way. So if you work that out, that should be partial x beta partial x prime of, and then x beta. Okay, so this is a different way of writing it. This is x prime alpha, x prime alpha in the subscript, and now you reverse the order of derivative. This is like expressing one quantity to the other quantity, like a change of variable. Now you get the inverse relationship and take the derivative the other way around. So okay, and they define like that, and this matrix is turns out to be similar, right? This matrix is but first we can talk about why we do that, because we if we do it like that, we can do that what we call the dot product. The dot product basically now is like you have the x prime alpha, the contrarian one, and then sum over the alpha index, sum over all indices of the covariant four vector. So we say that we do summation when one is superscript, one is subscript. So this is sum over that, and that defines the dot product. And from this, obviously, you can see that that is simply just sum over this times that, this times that. I mean, that's c squared t squared minus just the absolute value squared, right? That's just, and we know that there's a scalar. We start from that. We have to, this is a starting point of discussion that this like if set is to zero, it's just the location of the light sphere. But from this definition, we see that you can actually write it like this. You do this transformation, so it's for the first one becomes actually I should see this is the contrarian. The contrarian using this one is partial x prime alpha partial x beta, and then you have x beta. Let's write the x beta here. And then the covariant one is this one, partial x beta partial. This is the, I actually should not use beta because this is, I already used beta here. partial x gamma, partial x prime alpha, and then the x gamma. That's just substituting here, and that becomes like a chain rule. So if you do a derivative, take this derivative and then multiply by this derivative at g, and then you sum over alpha. Then this is like the partial x gamma, partial x beta, partial x gamma, x beta, this x beta, x gamma, right? And you know what this is? We did that many times. What this is? Take a this object. Remember that? That's just a conical delta. So it would be 0 if they are not the same. Obviously, they would be 1 if they are the same. So this is just a conical delta. But in this notation, the conical delta actually has one subscript and one superscript. X beta, x gamma. Okay, and finally, if you now sum over gamma, what we call contraction over gamma, then the gamma becomes beta. So this is finally just this x beta, x beta. So the two is the same. So the dot product of this four vector, the form in the k prime frame and the k frame is exactly the same. Okay, so they have this definition of covariant four vector. How you transform it, that will make sure the dot product is invariant. Okay, so that's the motivation why we define that. Okay, so now we define this covariant four vector. And what else? So now we can do the same thing. Any vector transform like this using this matrix as a covariant four vector, right? And now what is next topic is the introduction of this metric four vector, or metric tensor. Yeah. Okay. So again, this is the contraction between the space-time four vector. Get to this one, and this is for linear transformation, but for more general transformation, you want to keep it. It may not be linear. You want to consider a small increment. So what we call is ds squared. We defined that before. Ds squared. Therefore, this is c squared dt squared minus dx squared, right? And or you can write explicitly dx squared minus dy squared minus dc squared, right? And so that is defined by this small increment in the difference between two four vectors and the norm of the difference between two four vectors. And the general, you can write as a general way to write a summation of this, what we call a metric tensor, G alpha beta, but then sum of the x alpha x beta. So generally, this is this form. You just sum over different thing, different increment of this dx different component of that with this tensor, just sum over alpha, sum over beta. The result will be the scalar, which is this ds squared. And by comparing this with that, this, at least for special relativity, this G alpha beta, the metric tensor is simple because this is just 1 and 1. So this is the metric tensor for special relativity for inertial frame, transformation, or the space of an inertial frame. Okay, and we can define the metric tensor like that. And some people define with a negative sign. So this is negative, this is all positive. And this is just different convention. And the reason we introduce this language is that generally you can define a metric tensor different. You can define different metric tensors different than that. This is just for an inertial frame or what we call Minkowski space. So this is the metric tensor for a Minkowski space, which is very simple form, but for more general form, especially when you have gravity, then all this G, all the component of G alpha beta may not be zero, may not be that many zero, and maybe more complicated that you can, basically the geometry of the space-time becomes not more complicated, or we can say it's curved space-time. Okay, and so that's the reason we do that. But we are introducing this language just to write the equation in the help us to write the equation and the derived equation, right? And the property of this G gamma beta is that this is, we define this as covariant matrix. Hence, we can also define it like the contrarian G alpha beta and change all that to change the dx to covariant. So we can do that, and we know how to do that in this transformation, right? But for Minkowski space, that this is it doesn't matter because the covariant just changes the sign of the spatial part, so that's the G is still the same. And that is the good thing about the Minkowski space. The two tensor, the covariant and contrarian, they are the same, right? And so there are other property, but we probably will skip some of that because that may be too complicated for us. I mean, too much for us for now. We'll mention that if we need some other property. But some important property is that you can use the metric tensor to change from covariant to contrarian. So basically, like the space-time lines, you can write the covariant one as this G alpha beta and contract with the contrarian space. And you can check that that is correct for this Minkowski space, right? Because if this is like a matrix multiplication, you multiply this with a column vector of this. This is just CX, right? And obviously, you multiply this with that, you actually just change z to minus z, x to minus x, y to minus y, right? So that would be your covariant vector, right? And likewise, you can change covariant to contrarian, multiply by this contrarian matrix. If you do that, you can do the convert. So basically, this matrix tensor has another way to basically he has the operation, you multiply this by a vector, you can kind of changing the superscript, the subscript, or subscript to superscript, and that will be needed because in many cases whether a vector is in superscript or subscript is it's more convenient to change one to subscript or superscript. So you add the G to that. So we'll see some example maybe later. But that's just the property. Okay. What else? Yeah. Then we define another four vector by the. Now it's slightly different. We can define a four vector by the derivative. So this partial alpha. We are using it in a subscript. Basically, this is a short form of partial x alpha. This is a contrarian component. But then when you write it as a differential operator, this is in subscript because this is in. Okay, and therefore this is, you write it in component form. This is partial CT, and then you have partial Z in Jackson's partial X. Okay, or in the short forms. T, and this is just a gradient. Right. So that's a differential operator, differential four vector, or the gradient four vector. But this is in the subscript, but you need to pay attention that actually this is positive sign, unlike this one. This one has a negative sign, spatial part. This one has a positive sign. And likewise, you can define the contrarian gradient for vector. And in this case, it becomes that changes. So the contrarian of this gradient for vector actually has negative sign. So that is the reverse from the space-time for vector. Okay, that's something to be, mindful, because otherwise big sign errors here and there. Okay, so that is what we have. And also, once you define this differential four vector, you can combine them with other four vectors to do things like if you have like a scalar, so you have or you contraction with a four vector with another four vector with or the gradient of four vector by this gradient operation. So like partial by partial alpha, some four vector A alpha, right? And obviously that contraction will be it will be invariant because we already talk about that. This is basically a contraction between four vectors that is invariant. And write in component form, that would be partial A sub 0, partial C. And now this is subscript with a covariant, so that is actually positive. And this is gradient, and this is the spatial part. This is a contrarian, so it's positive, so it's divergence. Okay, and this is invariant. So we know that this will be a scalar. Okay, in the sense that it's independent of frame. The transformation is simple. It just doesn't change. Okay, and now we can use that to build up our four vector. If we found a quantity that satisfies an equation like that, then we can say that, and then this equals to a scalar, of a scalar, then you see that this A form a forward vector, right? And one simple example that we already saw in E and M is that we have the continuity of charge density and divergence of current density. This is just the continuity equation, and this is the conservation of charge. And the right-hand side is 0, which is obviously a invariant. Whatever frame is 0 is 0, right? So that's compare this with that, because we know that the gradient, this partial paucity and gradient form a four vector. It's actually a four operator, right? And this is the right-hand side invariant. So you see that the rho and j should form a four vector. In this case, we want to compare this form to add a c here, add the c in the numerator. So this four vector is the charge density and current density for this form where four vector. We can define that as this is j of this is contravariant as this is positive. Okay. Obviously, this is a covariant one. We just change the sign of j. Okay. So now we get one more, and then we're getting close to E and M quantity because this is charge and current density. Okay. So we know how to write charge and current density in four vector now. Okay. And before we do other things, we can also use a derivative to form other operator. Say, like if you contract like a covariant one with a contravariant one. By this form is obvious. You see that one is positive, the other is positive, negative, so it's positive square, c squared positive t squared minus, and this in the space of is just the usual Laplacian. Okay, so this operator is also covariant, and there's a name for that. I think people define it square or something like that. I think this is called the D'Alembert operator. Okay, and this is like the wave equation. If it is operate on the scalar field, then that's satisfy the wave equation. Okay, and so that for that we're getting closer. And 17. I mean 11.7 is a little bit more advanced topic of this, all this tensor notation. Actually, we are considered using that as to discuss what we call the Lorentz group. We are out of time. We won't do that. And 11.8 is an example of that interesting topic, but we skip that also. We go to 11.9 and build more four vector. Seems I'm missing one. Okay, okay, that's fine. Well, we'll go a little bit in the middle part of 11.9 first. So to build up another four vector, once we have this charge density and current density four vector, now we want to extend it to E and M quantity. The first thing you remember that in chapter 6 we derived the wave equation operate on the potential, and that the right-hand side would be the charge density and current density. Although in chapter 6 we have written those equations are written in SI unit, so you need a little bit of transformation to get to the Gaussian unit that Jackson is using now, but that shouldn't be too difficult. Basically, this is 6.15 and 6.16. No, it's fine. So this operator, you have 1 over c square plus square partial t square. The electric potential actually that equation, actually this is minus 9. Let me see if Jackson actually reversed the sign in here. So that's for Jackson. It's equivalent. So this 6.15 and 6.16 is the same as 11.130 and 131. So according to the new chapter, this is 4.0. This is in Gaussian units, so that's slightly different from the SI unit equation. And then the vector equation A. This is 4.2. And this is under what we call the Lorentz gauge or radiation gauge, right? And it's subject to a gauge condition. Again, this is in Gaussian unit. Right. Now we see that we already found out that charge density and current density for vector, form for vector. So this charge density, current density, or you can make it symmetric. It's divided by C multiplied by C. So this and that, the right-hand side components of all vector. Then you can see the left-hand side, whatever operate by this the Lambert operator should also form a four vector because this is invariant. The right-hand side is invariant. So the combination of phi and A should also invariant. So you can combine that and compare with that, and then satisfy yourself that the electric potential and the vector potential, the magnetic potential, form a four vector. Okay, because of rho times C and J, the combination of that form a four vector. And you notice that this is a Gaussian unit. So now phi and A has the same unit because you put it together. Right? Okay, so that is different from the SI unit. And that might be the reason why Jackson going back to Gaussian unit relativity chapter, because that seems to make more sense. Right. Another way to look at that, this is a forward case, use the gauge. The gauge is also satisfied. This is like what we said, right? And you see that this compare this with that equation, you see that phi and A should form a four vector. Okay, so anyway, that's what we have. And so this, once we have established this as your four vector, this is what the contrarian potential four vector. Then this equation, these two equations combined as the Lambert operator operates on A alpha is 4 pi C. Using tensor notation, these two equations in the single equation, instead of two equations, single equation operate on four vector. And the gauge transformation, a gauge condition is published. Okay, so that's that. Now we're getting close. Now, after you have potential, obviously the next step is to express your electric field and magnetic field into tensor form, into this tensor notation. And now we remember this one, but then let's figure out what the electric field and magnetic field should be. Now the electric field is, let's write down, electric field is, this is not the electrostatic, potential, so that is, you have a partial A, partial T terms. This is from chapter 6, if you remember. So you have vector potential and scalar potential and form the electric field. The magnetic field is easier. You just curl of A. That's okay. Now, now to that these operation doesn't seem to give you a doesn't seem to be easy to make either B or E or combination of them to 4 vector, because that doesn't match the form that we have here. Is partial T of the vector and gradient of phi, and like this is partial T of scalar or the and then the divergence of a vector. So this is significantly different, and also this curl is doesn't look like what we had before. So what we need to do is extend it a little bit and look at component by component first, right? And what we'll do is like consider each component and see if we have any insight or any suggestion what it should be. Like consider this. This is you have this electric field. You have CXY component. Like consider one at a time. So like E sub C, right? E sub C is this. It's actually the C is the one component, or whatever this is. This one component, and that equals to 1 over C. Now the partial A, partial T, the Z component, because this is the same vector, partial A, T, partial T, right? And minus this gradient also in the Z component. This is partial phi, partial Z, right? So that's the Z component. And let's write it in a little bit using our four vector notation. And remember this the gradient 4 vector. We actually want to write down the counter. We want to write down the counter variant first. This is the zero, so part 1 over C partial T is the zero component. So minus partial 0. And A sub C is this counter variant 1 in the one component, because this is phi A Z A X and Y, right? So this is partial 0 A 1, right? And for the phi component, this is this one. If this is minus, there's a minus sign, and this is C, which is the one component. So this is plus partial 1, and phi is the 0 component of this one, A sub 0. Okay, so then we can write it like this is E in the one component, whatever that is, the one component, right? And let's just keep it easy, right? And now this is 0, 1, and then you see there is symmetric. You exchange the two, get 1, 0, and change the sign. Okay, now we consider, and then at the X and Y component will be similar, obviously. Now we consider another component, say like again the BZ. Let's look at the BC component. PC will be, according to this, will be partial x a y minus partial y a. Right, this is just the standard curl operation, right? And then now we compare with this operation. Partial x is the second component, 2 component. Now with a negative sign, you have negative partial 2, and ay is the 3 component, right? Ay is the 3 component, so a3. And likewise, this is the 3 component. So partial 3, x is the second component. This actually is plus because that's a negative sign. So a2. Okay. So again, you have the 2 indices exchange and then change the sign. Okay. And now this other components of B also satisfy something like that. And now that gives us a suggestion that we define an object, what we call the electromagnetic tensor, electromagnetic field tensor, so F alpha beta. And the definition is partial alpha A beta and minus the reversing the 2 indices. Okay, so that is the. Now we define that, and obviously, because both the gradient and A, this potential 4 vector, they are all 4 vectors. So this combination is obviously also invariant with frame. So this definition will give you a tensor. Okay, and which is fine. We want to get the tensor. And now it's an anti-symmetric matrix because if you exchange alpha and beta, exchange the sign. So F beta alpha would be minus of F alpha beta, obviously, because you just interchange the 2 terms. Right? This is a total anti-symmetric matrix. So the diagonal component will be 0 because alpha you just set the 2 to be the same, so the 2 terms cancel. So diagonal term will be 0. A little out of time. Let's keep doing a little bit and finish this. And just write it out explicitly. You know that all the diagonal terms are 0. This is a 4x4 matrix, right? And the rest is you have 6 component. You have 3, 2, and 1. And the other triangle is just the negative of the other one. So you just need to work out this 6 component. And by this consideration, you know that this one will go to because it's CO1. This is CO1 component, and then you have a negative sign, so you have negative. Or that's just very easy. I mean, Jackson changed it to XYZ. This section is strange, but doesn't matter. XZ X1. That's the electric field, and then the column, the CO column, is just the negative of that. So we finish 3 of them. Okay, now the rest you need a little bit of thinking. So the 2, 3 component, which is the CO1, 2, 2, 3, CO1, 2, 3, CO1, 2, CO1, 2, 3, the 3 component. This is BC. 2, 3. Actually, negative BC. BC. Okay, and the rest you can use the same way to figure that out. So all time here, so I just CXY. This shouldn't be Y. CYX. This should be X. CYX. CY. BX. CX. CX is Y. Okay. And Likewise, this is xc is minus y, so this is dy. Or you can just do the Mueller minus dx. Okay, so you can fit all the electric field and magnetic component in this second rank tensor. So now we know that the electric field, magnetic field, they don't form four vector. They actually are components of a four tensor, 2x2, second rank tensor. And that is the what we call the field tensor now. And we can write down the Maxwell equation using this, and then figure out how you transform electric field, magnetic field by this tensor. Because once we have that, we know how to transform